Okay, so we are now going to start looking at linear congruence relations. Now, the big thing to get to is going to be the Chinese remainder theorem. That'll be a few videos from now. Got to sort of lay some groundwork. So what is a congruence relation? What is a congruence equation? So a congruence relation, let me just write what the notation is and then explain what it means. So if you say something like x is equal to r mod m, if we say something like x is equal to r mod m, what this means is that if we take x and divide it by m, the remainder is r. So what this means is if we take x and divide it by m, the remainder is going to be r. So if you think about like time, we might want to divide by 12. So right now, let's say it is 3 o'clock p.m. It's a little bit before then. Let's say it's 3 o'clock p.m. If I want to know what time it is 14 hours from now, 3 plus 14 is 17. If I do the remainder after I divide by 12, that gives me, I forget what I said, 14 plus 3, I think I said 14, that's 17, so it's going to be 5. So 14 hours from now, it's going to be 5 o'clock. And so that would be the remainder. If I wanted to do, 300 hours from now, I would do 3 plus 300, that gives me 303, and I take the remainder of that number after dividing by 12, and that's the time it's going to be 300 hours from now. And if you look in the book, this type of time thing is the exact motivation that the Chinese mathematicians were using to solve congruence relations like this. Okay, so I just want to point something out. It's going to be very important to us. There's something called the division algorithm. The division algorithm is it's the following fact. It's not really, I'm not going to really give it as an algorithm. I'm just going to tell you that, this is the fact, and then you can figure out an algorithm for yourself to sort of, produce the output. Anyways, so what the division algorithm says is that if you have two numbers, let's say x and m, then we can always write x as some integer k times m plus a remainder where r is less than m. And so this is pretty clear how you would do this. You would just add m to itself as many times as you need to get, so that if you did it again, you'd be over x, and then whatever the distance is between x and that value of k times m is going to be the remainder here. Okay, and again, this just says if you do x divided by m, it's going to be k with the remainder of r. So x divided by m is equal to k with the remainder of r. Okay, so like I said, eventually we're going to solve systems of linear congruences, but I haven't even given one linear congruence equation that we want to solve. So we're going to look at a congruence of the form a times x is equal to 1 mod m. Okay, I'm going to show you how we can solve this. I have to do quite a bit before I can even do that. An assumption that we have to make here, which we'll see why in a minute, is that the greatest common divisor of a and m is equal to 1. We want to show that we need to know that the greatest common divisor of a and m is equal to 1. In other words, they're relatively prime. If you look at the prime factorization for a and the prime factorization for m, there's no common primes in either one of those factorizations. Okay, now before we can solve this, we need an algorithm for how we can find the greatest common divisor of two numbers. So just kind of put congruence relations aside for a minute, put a pin in that, and let's figure out how we can find the greatest common divisor of two numbers. So I want to know how to find the greatest common divisor, the GCD of A and B. So I want to know how to find the greatest common divisor of A and B. Now here's a fact that I'm going to use but not prove. The GCD of A and B is equal to the GCD of A and B minus some integer multiple of A. And I'm going to be assuming that B is greater than A as well. Okay, so like I said, I'm not going to prove that, but it might be an interesting thing for you to talk about on one of the discussion posts. I didn't mention that. I didn't list that as an option for discussion question, but maybe I'll go back and add it. But even if I don't, and even if I hadn't mentioned this, you can always, come up with your own topics for the discussion post. So here's how we're going to do this. I'm going to explain how this algorithm will go, and then I'm going to illustrate it. So first, what we're going to do is we're going to use a division algorithm to say B is equal to K1A plus R1. And using this fact up here, what this tells us is that the GCD, let me kind of make a running thing here, the GCD of A and B is equal to the GCD of A and R1. And that's just because R1 is equal to B minus K1A, which is like this exact thing here, except there's not a one subscript. So that's why the GCD of A and B is equal to the GCD of A and R1. Okay, and notice also by the Euclidean algorithm here, or by the division algorithm, R1 is strictly less than A. So this is now, again, it's the same sort of symmetric here. B is less than A, R1 is less than A, which is less than B. So now we have to find the GCD of a pair of smaller numbers. And we can say A is equal to K2 times R1 plus R2, where R2 is strictly less than A1. And so now this, the GCD of A and R1, is equal to the GCD of R1 and R2. And R1 again is strictly less than A, R2 is strictly less than R1. So now this is the GCD of two smaller numbers. Okay, now we're going to continue this pattern until it ends. We're going to continue this pattern until it ends. What do I mean by ends? Now, it's not always good. It's going to take several, many steps. It could take infinite, not infinitely many steps, but for any end, it could take that many steps. But let's just say it ends on the next step. And when I say ends, I mean this happens. Let's say R1 is just equal to a multiple of R2. Let's say R1 is just equal to a multiple of R2. When this happens, what it means is R2 is the GCD. Okay, it means that R2 is the GCD. Because down here, again, if you look at the GCD of R1 and R2, that's the GCD of A and B. Okay, so the GCD of A and B is equal to the GCD of R1 and R2. If we get down to this step right here, this says that R1 is a multiple of R2. So the GCD of A and B is equal to the GCD of R1 and R2. But this here says that R1 is a multiple of R2. Okay, if R1 is a multiple of R2, well, what is the greatest common divisor of R1 and R2? It has to be R2, right? Anytime you have a greatest common divisor of two numbers, the greatest common divisor has to be less than or equal to the smallest one. If one number is a divisor of the other, and that's going to be the greatest common divisor. Okay, so that's the greatest common divisor. Okay, so let me illustrate this with an example. So let's say I want to find the GCD of 12 and 70. Don't know why I didn't toss the bad marker out. Okay, so 70 is going to be equal to 5 times 12 plus 10. Okay, so what this says is the GCD of 70 and 12 is equal to the GCD of 12 and 10. So 12 is equal to 1 times 10 plus 2. Okay, so the GCD of 70 and 12 is equal to the GCD of 12 and 10 is equal to the GCD of 10 and 2. Now 10 is equal to 5 times 2 plus 0. So therefore the GCD of 70 and 12 is equal to 2. Okay, let's modify this slightly. I just want to show you what's going to happen when the GCD is 1. So let's look at the GCD of 70 and 11. Let's look at the GCD of 70 and 11. So 70 is equal to the GCD of, so the GCD of 70 and 11 is equal to the GCD of 11 and 4. 11 is equal to 2 times 4. 2 times 4 is 8 plus 3. So the GCD of 70 and 11 is equal to the GCD of 11 and 4 is equal to the GCD of 4 and 3. Okay, so then 4 is equal to 1 times 3 plus 1. Okay, so the GCD of 70 and 11 is equal to the GCD of 3 and 1, and 3 is equal to 3 times 1. So the GCD of 70 and 11 is equal to 1, which of course we can inspect that because we know 11's prime and 70 is not a multiple of 11. 11 does not divide 70. Okay, so I know there's a huge point of discontinuity there, and now there's nothing here on the screen, and the reason is because I had started to move on to a different problem to show you how I can solve this, but I actually just want to stop here after illustrating the Euclidean algorithm, and then once in the next video I'm going to show you how we can use that to solve this congruence relation there. Okay, so there's going to be a couple of videos of kind of background information that we have to get to before we even get to stating the Chinese remainder theorem, but it's a very important theorem, and so I hope it's going to be worth it.